Hello, my name is Immo Niskanen, and this presentation is about virtual fatigue testing. This presentation is largely based on my bachelor's thesis. So let's get into it. Virtual fatigue testing, or VFT, is important because, as we all know, fatigue is often the defining factor of a component's life. Those components could be like machine components or structures like bridges, and fatigue is often the reason for the failure of these structures, and therefore researching is important. And virtual fatigue testing offers several advantages over traditional fatigue tests, to which we will get into shortly. And many fatigue models have been developed to model the phenomenon, and we will in this presentation look at one of these models and the results produced with it. And virtual fatigue testing could be defined as testing of high accuracy digital twins, which are very accurate digital versions of real test specimen or components. And the advantages that virtual fatigue testing has and why use virtual fatigue testing. The main reason for virtual fatigue testing is the reducing and removing the need for physical experiments, as those are expensive and very time consuming, and virtual fatigue testing also allows the accurate modeling of fatigue mechanisms on a microstructural level, which is really not possible to the same extent with traditional fatigue tests. And virtual fatigue testing also has commercial uses. It can be used for component design, process, and material optimization. And here we see a simple graph about using virtual fatigue testing for material optimization. We can start here on the loop by choosing desired properties, what we want from material, calibrate those properties into the fatigue model we have, simulate the model, and analyze the results of the simulation. And based on the fatigue behavior, we can then further enhance the properties we desire from the material and repeat the cycle again. This is a very simple example how to use virtual fatigue testing for material optimization. And a little bit about fatigue as a phenomenon. Cyclic loading is what enables the initiation of fatigue crack, and fatigue life is defined as the number of cycles needed for the failure of the specimen. This fatigue life can be divided into two parts. First one being the initiation and propagation of microcrack, and the other one being the growth of the microcrack to a macrocrack, and the growth of that macrocrack to the failure of the specimen. And the cyclic loading is what causes dislocations to form into the material, and these dislocations then pile up into certain parts of the material, which then causes local plasticity. And usual regions for this plasticity to accumulate to is around defects like inclusions and areas with favorably oriented grains and such. And this accumulation of plasticity is then what makes the fatigue crack initiation possible. And high cycle fatigue is especially interesting for us, as the understanding of it is necessary for designing fatigue resistant components and machine parts, as those machine parts usually fail in the high cycle fatigue region. And high cycle fatigue is caused by small, not visible elastic strains in the cyclic loading. Although the strain of the component is elastic, there still some plasticity occurs in the material, which then enables the fatigue failure. And the crystal plasticity model we shortly look into allows the accurate investigation of these high cycle fatigue mechanisms. And a little background about fatigue models and their history. The beginning of fatigue modeling can be thought to be in the 1940s when the Miner's rule was created. This Miner's rule allows the prediction of remaining life of the component based on the damage accumulated on the previous cycles. And after Miner's rule, there has been a lot of these equation type empirical models, probably one of the most notable being the honor model by Chapotson and Lesne, developed in the 1980s. And these type of model are used because of they are easy to use and not very demanding computationally. But what we are really interested in is the development of computational micromechanics of fatigue, which had their start in the 1980s. For example, Needleman and his colleagues started to investigate the effects of fibers in composites and the effects of grain boundary cavities and such. And as time goes on, the models obviously get more advanced. In the 1990s, the model started to include effects like the stochastic nature of microstructures and grain orientations and such, and the overall stochastic nature of fatigue. And crystal plasticity models started to gain a lot of attention in the beginning of the 2000s, although the theoretical basis for them has been there since the 1970s, and some models have been developed through the 90s, but they really took off in the beginning of the 2000s. And the reason for this takeoff is that the crystal plasticity models allow the accurate investigation of microstructural properties on the fatigue behavior and like micromechanical mechanisms of fatigue, such as interactions between grains and such. And this is why they are one of the most important model types today. And the newcomer in the field is phase field modeling, which has gained a lot of attention in the past decade, and the reason for this attention is that phase field models are very efficient in problems with sharp interfaces, such as fatigue crack propagation. In this presentation, we look at one crystal plasticity model. This model is developed by Lindroos et al. In 2019, and for this case the model was transformed for the theory of small deformations, and the damage part was not included, as the damage part makes the model very demanding computationally, and it was not seen necessary for my bachelor's thesis, so it was removed. And this model was then used in Zset for finite element simulations, and as the result of the damage being removed, we can soon see that the damage or the stress strain curves do not turn downwards because of the lack of the damage. And here are the equations behind the model, which we will not go into detail in this presentation. And about the materials used in the test, here we can see a 100 grain prior austenite-like microstructure, and below it we can see a microstructure with a martensitic substructure and a round inclusion in the middle. There were three variations of this microstructure, this one being 100% prior austenite grain size inclusion, there was one smaller with 50% and one larger with 200%. And well, these microstructures were used in tensile tests and cyclic loading, and both of these were given the values of high strength martensitic steel. And then we get into the results. Here we can see the tensile test results for the 100 grain per year austenite-like microstructure. Here is the stress strain curve. It looks like a very typical stress strain curve. It yields at about 700 megapascal, and the test was done to 5% strain. And here we can see that the curve doesn't turn downwards because there is no damage included in the model. But we can see that the model is capable of producing these typical stress strain curves, and below it we can see the microstructure's plasticity after the test. We can see very strong strain localization here, middle of the left side, and here diagonally from the upper right corner. And this localization of plasticity is due to the favorably oriented grains in these regions. And then we get into the microstructures with inclusions. Here we can see all the different size inclusions, and they were used in same kind of tensile test to 5% strain, and the stress strain curves are shown here. We can see that although all these microstructures yield at pretty much the same point, the one with larger inclusion has higher strength after yielding, which is to be expected because as the inclusion gets larger, the elastic differences between it and the material matrix get more significant. And here we can see all the microstructures after the test, and the effects of elastic differences are again seen here, as for the smallest inclusion the plasticity distributes fairly evenly into the microstructures, and as the inclusion gets larger, the localization of plasticity is more significant, and well, it doesn't distribute as evenly into the material. And this is also seen in these distributions of plasticity, and we can see that as the inclusion gets bigger, the distribution gets wider, which is caused by the elastic differences. And here the effects of the inclusion's stiffness was investigated. This was done with 5 different inclusion stiffnesses, and the 100% prior austenite grain size inclusion microstructure was used here. The stiffnesses went from 80 to 400 gigapascal, and here we can see stress strain curves for all of them. We can see that they are pretty much on top of each other, although the stiffer inclusion is slightly higher than the others, or the strength increases slightly with the stiffness increasing, which is again to be expected because of the elastic differences getting more significant between the inclusion and the matrix. And here we can see the 80 gigapascal microstructure compared to the 400 gigapascal microstructure after the or the microstructure with 80 gigapascal stiffness inclusion and 400 gigapascal stiffness inclusion compared, and we can see that with 80 gigapascal the plasticity distribution is more even, and with 400 the elastic differences are more significant, and the localization of plasticity is therefore also more significant. And this is also seen in this plasticity distribution. We can see that as the stiffness increases, the distribution gets wider. And about cyclic loading, here we can see the results of the 100% prior austenite grain size inclusion microstructure with 400 gigapascal stiffness for the inclusion used in the cyclic loading test with 1% strain amplitude, and the result looks like a very typical hysteresis loop of cyclic loading. We can see clearly the effects of hardening in the material as the loop takes few cycles to stabilize, and this effect is also seen here in this stress time plot as the stress amplitude gets slightly higher for the first few cycles. And here we can see the microstructure after the test. We can see that the plasticity localizes mostly into the material matrix, and this is due to the fact that the inclusion is perfectly bonded to the material matrix, and the strain amplitude being fairly large, it causes a lot of plasticity into the matrix. With lower strain amplitudes and with if the inclusion was partly detached or something, the plasticity would accumulate more in the immediate region of the inclusion. And these results were validated with the test of effects of mesh density. The effects of mesh density were tested with these 4 different meshes and third grain prior austenite like microstructures as we see, like the one we saw before, and the microstructure was smaller because this densest mesh is very dense and therefore very demanding computationally. But all of these different meshes were used in a tensile test, which results we can see here. The curves for all of these are on top of each other, and from this we can conclude that the mesh density has pretty much no effect on the global behavior of the microstructure. And on the other hand, on the local level, some effects are seen, and for example here on this plasticity distribution curve, we can see that the denser mesh allows more accurate localization of plasticity, and therefore these spikes form into the distribution. And well, there are some differences between the different mesh densities, although the shape are somewhat same. More significant differences are seen in this stress distribution. We can again see the more accurate localization by the densest mesh. And from this we can conclude that although the mesh density has pretty much no effect on the global behavior of the microstructure, some effects are seen on the local level. And for summary, virtual fatigue testing offers an effective tool for understanding and researching fatigue as a phenomenon. It also has some commercial uses. For example, it can be used for designing fatigue-resistant components and material optimization, and help with the design process overall. And the crystal plasticity model we looked at here is capable of producing realistic results and realistic fatigue behavior, and also is capable of modeling the micromechanical effects of fatigue. Thank you.